In the sky, gazing far into the night, I raise my hand to the fire, but it's no use, 'cause you can't stop it from shining through. It's true, baby, let the light shine through. If you believe it's true, baby, won't you let the light shine through for you. In the sky, gazing far into the night, I raise my hand to the fire, but it's no use, 'cause you can't stop it from shining through. It's true, baby, let the light shine through. If you believe it's true, baby, won't you let the light shine through for you.
Take a look around, and you'll find this wonder metal everywhere, in everything from screen doors to jet planes. Aluminum has so many applications because it's light and strong, and it's corrosion and crack resistant. Producing aluminum is costly, but it saves money over time. Aluminum, so widely used today, and the world's most abundant metallic element, does not occur in a natural state. The most available source of aluminum is actually bauxite. Bauxite is mainly mined in tropical countries. The aluminum atom in bauxite is bonded to oxygen molecules. These bonds have to be broken by electrolysis to produce pure aluminum. Bauxite is carried by rail to the plant where it will be crushed. Then, through a chemical transformation called the Bayer process, alumina is extracted. This is then roasted in calciners to eliminate all moisture. This is the reduction facility. This plant has 432 pots through which a powerful electric current will be passed to produce electrolysis. An overhead crane dumps alumina into the pots. Then the electric current from the anode passes through the alumina that we see here at the bottom of the pot. Via the process of alumina reduction at 1742 degrees, the anodes lose volume and will have to be replaced. It's a continuous operation. Each anode has a lifespan of about 20 days. Spent anodes are recovered from the pot with this overhead crane and carried off to be recycled. They clean the aluminum rods, which will then be reused. Here we see the crust formed atop the anode. When the anodes are replaced, the accumulated impurities have to be recovered from the top of the pots. This is accomplished with these pincers. Then a new anode is inserted into the alumina and electrolysis continues. The electric current breaks the molecular bonds. The heavier aluminum collects at the bottom of the pot, while the oxygen bound to fluorine is released as a gas, which is drawn off and treated. The liquefied aluminum remains at the bottom of the pot. It has to be recovered in this huge crucible with a tube. The tube is dipped into the bottom of the pot, and a vacuum system draws the molten aluminum from the crucible. The aluminum is recovered in a short time. Air is vacuumed from the crucible by a flexible pipe held by an operator. The tube is finally withdrawn, and the overhead crane dumps another quantity of alumina into the pot. Thus, the aluminum fabrication process continues uninterrupted. The crucibles filled with molten aluminum are transported to the casting house. Their contents are poured into holding furnaces that have a capacity of 60 tons. In these very hot furnaces, the molten aluminum is stored to await casting. Finally, casting begins. The aluminum can be semi-continuously vertically cast, producing ingots, sheets, or billets, or it can be directly cast into semi-finished products. The cooling of aluminum pieces is accelerated by water sprays. The large rectangular ingots, which can weigh up to 25 tons, will head for hot rolling and eventually will be fabricated into products like aluminum foil. From 4 to 5 tons of bauxite have produced 2 tons of alumina, which in turn produces 1 ton of aluminum. This particular plant produces 200,000 tons of aluminum annually. Some other facilities can turn out as much as 400,000 tons.
Pro family really is a quite remarkable engineering achievement. It's truly the result of years of hard work, of innovation, I think driven by this obsessive attention to every detail. And this is particularly evident in the enclosure. I mean, traditionally, notebooks are made from multiple parts. But the problem is when you have multiple parts, you add size and weight, and you increase the opportunity for failure. And the huge breakthrough that we had was to replace all of those parts with just one part. And that one part we called the unibody. We figured out a way of being able to make the notebook fundamentally thinner, lighter, more robust, and with sort of a degree of fit and finish that we've never even dreamed of before. And the only way to make that one part was to machine it from a single piece of aluminium.
Aluminum was the ideal choice for this product because it provides us thinness and lightness that we want in the portable category, great strength-to-weight ratio, also provides us some really nice options from a finishing perspective. The beginning of the unibody starts with a solid block of aluminum. Then we go through an extrusion process, which is kind of like how you make pasta. And the output of that goes through 9 separate milling operations. We take a part from solid block down to the finished, finely detailed part that has all of the features that we need to go off and assemble the new MacBook Pro. If you have the expertise to do that machining correctly, you can achieve an assembly method that is simple enough that we can get it right every single time.
Machining enables a level of precision that is just completely unheard of in this industry. We have been so fanatical in the tolerances of how we machine and build these products. In many ways, I think it's more beautiful internally than it is externally. I mean, I think that testifies to just our care. I mean, just how much we care.
The next time you buy a canned soft drink, consider this. The aluminium tin can will always be recyclable. Unlike plastic, aluminium never deteriorates, no matter how often it's melted down and used again. Aluminium cans are so lightweight that it's hard to believe that they're made from a huge roll of aluminium sheeting that weighs 9 tons. The sheet is about 1.5 meters wide, and a roll like this is long enough to make 750,000 drink cans. The sheet feeds into a press that punches out round pieces that'll be formed into cans. The punch press actually performs 2 operations. It punches out a disc 14 centimeters in diameter, then bends it into a cup. What's left of the sheet gets compacted and sent back to the aluminium factory, where it's recycled into new rolls. The cup goes into a machine called the Draw and Iron Body Maker. A tool draws out the aluminium, forming the body of the can. The tool is lubricated so it won't tear the aluminium while stretching it. The lubricant also acts as a coolant because the aluminium heats up as it's being worked. Once the body is formed, a trimmer cleans and straightens the edges. Now the cans move along, upside down on the conveyor belt, over to the washer. The washer performs a 6-stage cleaning. The first 2 washes are in hydrofluoric acid at 60 degrees Celsius. The last 4 washes are in deionized water, neutral water with no pH, also at 60 degrees. The cans come out of the washer and go under the hot air dryer. They're now shiny because the hydrofluoric acid wash removed a thin surface layer of aluminium. Next, a roller passes over the cans, coating the bottom rims with varnish. This coating allows the cans to slide easily on conveyor belts and in vending machines, and shows up as a blue ring under an ultraviolet light. The cans are now ready to be printed. This rotation printing system can apply up to 5 colours, one at a time. Then a layer of varnish is applied to protect the ink. Even in slow motion, it's a high-speed operation. And here's the actual speed: 1,800 cans per minute. Next, the cans fly through an oven that instantly hardens the ink and dries the protective varnish. Next, the machine sprays a water-based varnish on the inside of the cans. This creates a barrier between the drink and the aluminium, so the drink won't end up tasting like metal. It also prevents the aluminium from being eaten away from the inside by the acid in carbonated drinks. Next, the cans go through a machine called the necker, which forms a 5-centimetre neck on the can. This is done gradually in 11 steps, so as not to puncture the paper-thin aluminium. The next machine, called the flanger, forms a curved-over edge at the top of the can, which will later attach to the pull-tab cover. The cans pass through a sophisticated vision system that photographs the inside of each can. Any can that doesn't meet standards, that has a bump or some ink inside, is sent back for recycling. From here, they're shipped to the drinks company, which fills them and then attaches the pull-tab cover. So now you know, you can start the whole process off by recycling your cans.